now what we want to look at is another topic that's used quite frequently in industry when they're generating power and using part of the steam for other purposes in processes. So in this purpose, some of the steam is used, some of steam used for process heating. I could use it for building heat. I could use it in manufacturing, pharmaceuticals. I could use it in having heat go into reactors. And then we use the rest for power generation. Building heat, manufacturing, and then in the balance for power generation. So if I look at, so the context is I have a facility, I need it maybe for building heat, maybe I have a pharmaceutical processing where I need heat for the chemical reactions for the pharmaceuticals, and so I need heat. If I need enough of it, then it's worthwhile generating power as well, and so I have this idea of cogeneration. So I'm doing it for multiple purposes. And so let's look at a diagram for this. I'll do a diagram over here. So we'll have a steam generator. Going to a turbine. And then it'll go out of the turbine. So it'll go out of the turbine, and then it'll go into another turbine. So I have T2 and T1. So at this point, I'm not using it for cogeneration. So at this point, it's going here, and I'm extracting some. It's going to go through a control valve. And then it's going to go into process heat. So I'm going to have process heat. And so this will be at state 3. And we can call this Y1. So I'll have a certain amount that comes out Y1, and the rest continues on. And so it's state 3, so it's still state 3 here. So it comes in at state 2. At state 3, we take some out. The rest goes through turbine 2, goes out of turbine 2 into a condenser. So it comes out at state 4, into a condenser, and out at state 5. And what happens with the process heat, I need to recover this, so I'll have the drains come back. So I'll just show this as a drain coming back at state 6. So it's going to come back, and we need information about that. So now I have the Y1 coming back in, and then this goes back to the steam generator. So it's state 5, state 1. And we have a TS diagram. State 2, go down to state 3. And we're going down to state 4, over to state 5. We have a pump to state 1. And what happens here is this, we're going to draw a dotted line. I don't know what's going to happen. We typically have this come back, we assume, as a condensate at atmospheric conditions or something like that. So then we have our Y1 coming back at state 6. And often state 6 we assume is like state 5. It may be slightly different. And because this has two different purposes, we have something called the utilization factor. capital, I don't know, they use a capital Y, CG for cogeneration, and that's equal to W dot net over Q dot process over Q dot in. So it's the old efficiency idea, what you want. So what I want is process heating, I want to generate power, and what does it cost, the fuel coming in. And this is the utilization factor that we have. So now what I'd like to do is look at example 15.8 on page 572. And we'll refer to this diagram. I've got to get rid of some of the diagram, but we'll see how little I can get rid of at this point in time. So example 15.8. Page 572. And so at state 2, we have T2 is equal to 10 MPa. T2 is 500 degrees C. Seems to be a popular temperature with me. M dot 2 is equal to 6 kilograms per second. So it's telling you at this state we have 6 kilograms per second, and it's saying that at state 3, P3 is equal to 500 kPa. M dot 3 is equal to 3 kilograms per second. And now we go through, we can look up and find out what the H's are, so that's done in the problem. H2 is equal to 3376.5. H3 is equal to 2654. H4 is equal to 2089.9. H6 equals H5 is equal to 191.8. And H1 is equal to 201.9. So we have these enthalpies. We have these enthalpies, and the problem statement said that the drains came back at 10 kPa, so at the temperature associated with 10 kPa. And so with this, if I look, what is Y1? So in this case, we were given the mass flow rate. So I was given that M dot 3 was this, and M dot 2 is this. So Y1 is the fraction that's this. So the total amount is 6, the fraction withdrawn is 3, so Y1 is 0.5. So Y1 is 3 over 6, 0.5, and obviously 1 minus Y1 is 0. And so now we can go through and solve for the turbine work. I'll erase the far part and leave the TS diagram. So WT is equal to everything goes from H2 to H3. So 100% goes from 2 to 3. We withdraw Y1. 1 minus Y1 goes between 3 and 4. So if I substitute in, we have that WT is equal to 1004.6 kilojoules per kilogram. You can substitute in the numbers and just check on that. WP is equal to H1 minus H5 is equal to 10.1. So W net is equal to WT minus WP is equal to 994.5. Q in, Q process, so for the process, we have Y1 and we have this delta H between 3 and 6. So Q process is equal to 1231.1 kilojoules per kilogram. And Qn is equal to H2 minus H1. So Qn is equal to 3174.6. And we can find the utilization factor is W net plus Q process, oops, over Qn. So this is equal to 994.5 plus 1231.1 divided by 3174.6. So the utilization factor is equal to 0.701. And so what happens here is that I was able to use this steam. So if I just used process heating and I didn't have any work done, I would have a much lower number. And so because I have both going on, the utilization factor is much higher. Sometimes Q dot process is defined. So let's say Q dot process equals 3000 kW. So it tells you what you want the process heat to be, and this is equal to M dot process times H5 minus H6. The numbers refer to this example problem. And this is equal to, so I'm not writing down low, so we'll raise it up a little here. Repeat that. So we have Q process is M dot process times H5 minus H6. And M dot process is Y1 times this initial steam flow rate. So Y1 M dot S times H5 minus H6. And so sometimes rather than being given the mass flow rates, which we were, very often you're told how much heat you need, then you're going to solve for your mass flow rate of the steam. So that you have practice on this as well for homework, do 1545 and 1547.